Hello and welcome back to this course. Last session we talked about orthogonal polynomials. We know that orthogonal polynomials play an important role in approximation theory and spectral method. We investigated some important properties of classic polynomials such as Jacobi polynomials, Hermite and Laguerre polynomials. In this session, I'm going to talk about Bessel functions. And after that, I want to investigate some properties of these orthogonal polynomials to obtain the approximate solution of fractional differential equation. So in this session, I should give you some preliminary definition and theorem about fractional calculus. Bessel functions, first defined by the mathematician Bernoulli and then generalized by Bessel, and they are the solution of these differential equations. Bessel function of the first kind of order n denoted by Jn of x and has these series expansion. We talked about at the first session. Also, we have a theorem here, and it's about the generating function of Bessel function. The generating function of Bessel function of the first kind can be obtained from this equation. You can see this series is from -infinity to infinity. Bessel functions are orthogonal polynomials too, and orthogonality relation for the first kind Bessel function can be obtained from this equation. Integral 0 to 1. So these functions are orthogonal on interval 0 and 1, 0 to 1. The weight function is x. Gn of chi ix times gn chi, here is j, jx. So it's different from some other classic orthogonal polynomials. It's equals to this term. And now I want to show this equation to you. We know that the generating differential equation for Bessel function is equal 0. And now I want to show you this property. Integral 0 to 1 x jn chi ix jn chi jx dx. First, I want to show you if chi I opposite chi j, this integral equals to 0. Then for chi I equals to chi j, we show that that theorem satisfies. Okay, suppose that gn of chi ix and gn of chi jx be Bessel functions. Here, chi I and chi j are the roots of Bessel functions. So we know that Bessel function denoted by Jn of chi I or chi j equals to 0. Okay, Suppose that gn of xi ix and gn of xi jx be Bessel function, so they satisfied in this equation, and we have x2 t jn of xi ix plus x d the derivative of jn xi ix plus here we have xi ix, so here we have xi I2 x2 minus n2 gn of xi ix equals to 0, and we have this equation for gn of xi jx2. Xi j plus x derivative of jn xi jx plus xi j2 x2 minus n2 jn of xi jx equals 0. We can write this equation as this equation: x the derivative, this term x the derivative of Bessel function of order n of xi ix plus xi I2 x2 minus n2 jn of xi ix equals 0. It is simple. You can obtain from these two terms. And also x, the derivative of x times the derivative of jn xi jx plus xi j2 x2 minus n2 jn of xi jx equals 0. No. Now, by multiplying this term by 1 divided by x jn of xi jx and multiplying this equation by 1 divided by x jn xi ix and substituting this equation, from this equation we obtain xi I2 minus xi j2 x j Bessel function of xi ix times Bessel function of xi jx equals to 0. Now, by using this fact that we know that u dv the derivative of v to the x equals to the derivative of uv minus the derivative of u respect to x v. We can write minus jn xix x the derivative of jn jx minus j. Jn is correct. Jn ix x jx plus x plus this term. We use this equation for this part, and we have this section xi2 minus xj2 x jn j x j ix equal 0. We can omit these two terms, so we have this equation. Now, by integration from 0 to 1, from the equation we have this equation Jn of Jx x Jn ix minus Jn integral 0 to 1 x jn ix jn jx dx. By integral from this equation, here we have the derivative of this part, so integral from 0 to 1 can be this section, and for this section we have similar property, and we can write this. Here we suppose that I opposite to j, and we know that I and j are roots of Bessel function. So for this part in 0 and 1, we know that it can be 0. Also for this part, because of the property of the xi, and suppose that xi opposite to xj. So we have integral 0 for this integral 0 to 1 x jn xi x jn xi jx dx equals to 0 for xi opposite to xj. Okay, so it remains to prove that for xi equals to xj, integral 0 to 1 x times jn xi x, we can write xi equals to xj equals to xi jn xi x, or x equals to this part, half the Bessel function of order n plus 1 xi to the 2. Okay, we know that the generating differential equation of Bessel function is that, and for Bessel function of order xi x, we have x plus xi2 x2 minus n2 y equals 0. By multiplying the derivative of y on the both sides of this equation, we can write 2x, the second derivative of y, times y prime 2x 2 plus xi2 minus n2 2 y prime equals to 2. And we can write this equation this equation as minus 2 xi2 x y2 equals 0. Okay, this equation is equivalent with this equation. Now, by integrating from 0 to 1 from this equation, we have x to the 2 y prime to the 2 minus n2 y2 plus xi2 x2 y2 from 0 to 1 minus 2 xi2 times integral 0 to 1 x y2 dx equals 0. Now, by replacing y jn of xi x on this equation, we can write x2 dx the derivative of Jn of xi x to the 2 minus n2 times Jn of xi x plus xi2 x2 Bessel function of order n of xi x to the 2 from 0 to 1 equals to 2 xi2 times 0 to 1 x Jn of xi x to the 2 dx. We have this part, integral 0 to 1. It is weight function, Jn times Jn. We want to show that it can be like the theorem. Okay. In this part, in this section, we know that xi is a root of Bessel function. So for this part, we have 0. In this part, we have 0, 2, because for 0 to 1. It remains this part. It's derivative of Bessel function of order n of xi x. But we have a theorem here, and we want to use it for the derivative of Bessel function. And it is the derivative of Bessel function can be obtained from this equation. And I give you a reference that you can find the proof of this theorem. By using this equation, this theorem, in this part, we can write this 2. Here we have x2 x2, the derivative of to the 2 to xi2 we have integral 0 to 1 x Jn of xi x to the 2 dx equals to xi2 from 0 to 1 by substituting this part in this part. Okay, and we know that Jn of xi for x equals 0 and 1 is 0. So we have only this part. Jn plus 1 on 0 is 0, 2. But Jn plus 1 on xi, it's not 0. So we can write xi2 Jn plus 1 of xi times Jn plus 1 xi. We can omit this and we have Jn plus 1 of xi to the 2. And theorem, and the proof of theorem complex. So here, pay attention, Bessel function has this property. They are orthogonal on interval 0 to 1 on their roots. It's not similar to other orthogonal polynomials such as Jacobi polynomials, Hermite polynomials, and they have some special orthogonality properties. Okay. In this section, I want to talk about fractional calculus, and I want to give you some definition about fractional calculus. First, we have a definition here, a Cappato fractional derivative. The Cappato's fractional derivative of order alpha. Here, alpha can be a non-integer, for example, half, third, and we have fractional differential equation, fractional derivative, and fractional integral. And we say the Cappato fractional derivative of x equals to this term, 1 divided by gamma is a gamma function, gamma of n minus alpha times integral 0 to t, this term. For Cappato fractional, we have the derivative of order n, this section, in the integrand. And here, alpha is between n minus 1 and n, and it equals to n. We say that alpha is the order of the derivative and n is the smallest integer greater than alpha. Also, we have another definition here, the Riemann-Liouville fractional integral. The Riemann-Liouville fractional integral of order alpha can be defined as this equation. It is clear when alpha equals to 0, it will be x of t. But for alpha bigger than 0, we have this definition for Riemann-Liouville integral fractional integral operator. For Riemann-Liouville fractional integral, we have this property and we use it a lot. The Riemann-Liouville integral of order alpha of x to the nu, here nu is bigger than minus 1, we have this term. And now I want to show it to you. Okay, here I want to give you some reference for obtaining, for proving this theorem, and it's this book, Special Functions by Bell. A good book, and you can find a lot of information about properties of orthogonal polynomials and Bessel functions. And another book is Orthogonal Polynomials and Special Functions by Askey. This is another book about orthogonal polynomials and special function and It's a very good book too. Okay. I want to show you Riemann-Liouville integral of order alpha of x to the nu. I want to show you it is gamma nu plus 1 divided by gamma nu plus alpha plus 1 times x to the nu plus alpha for nu greater than minus 1. From the definition of Riemann-Liouville integral, we know that Riemann-Liouville integral of order alpha of function fx can be obtained from this formula. 1 divided by gamma of alpha integral 0 to x minus 2 minus tau to the alpha minus 1 f of tau d tau. Okay, by using this definition, we can write Riemann-Liouville integral of order alpha of x nu is 1 divided by gamma of alpha integral 0 to x minus 2 to the alpha minus 1 f of tau. Here we have tau to the nu d tau. Now here, by changing the variable, tau equals xs. We have d tau, the derivative of tau, x ds. So here we have 1 divided by gamma alpha integral here. When tau is 0, s is 0. When tau is x, s is 1. X minus tau, here we have xs to the alpha minus 1. Tau xs to the nu and d2 x ds. So we have gamma nu integral 0 to 1. We can write x to the alpha minus 1 minus s to the alpha minus 1 and x nu times s nu, s to the nu times x ds. So we can write x to the alpha minus 1 plus nu plus 1 alpha plus nu divided by gamma alpha integral 0 to 1 minus s to the alpha minus 1 s to the nu ds. And we know that we can write here nu plus 1 minus 1. And from the definition of beta function, we know that it is beta function of alpha and nu plus 1. So we have integral Riemann-Liouville of order alpha of x nu equals to this part, x to the alpha plus nu divided by gamma of alpha. Gamma function of alpha and nu plus 1 from the definition of gamma alpha is gamma alpha, gamma nu plus 1 divided by gamma of alpha plus nu plus 1. We can omit this and we have x to the alpha plus nu times gamma nu plus 1 divided by gamma alpha plus nu plus 1. And we can prove it. We use this property very much in fractional calculus. Also, we have similar this property for kappa 2 derivative of x nu. And I want to show you it too. So here you can see the definition of gamma function, and beta function is important too. Okay. Another property of fractional differential that I want to show you is that this. Kappa 2 derivative of x nu of order alpha is for nu less than, this is the selling integer part of alpha is 0, and for nu bigger than the selling integer part of alpha or equals to, it can obtain from this formula. Minus alpha. And now I want to show it to you. Okay. From the definition of kappa 2 derivative, we know that it is clear. I want to show it to you. The kappa 2 derivative of order alpha of f of x is equals to gamma 1 minus alpha times integral 0 to x, the derivative of f of 2 divided by x minus 2 to the alpha d 2. Okay, now we want to find this. So we have the kappa 2 derivative of fx of order alpha. Here x is x nu, f is x nu, is 1 divided by gamma of 1 minus alpha integral 0 to x. The derivative of f is nu x to the nu minus 1 d2 x minus 2 to the alpha. Here again, by changing the variable, x equals to 2 equals to xs, 2 equals to xs, and d2x ds we can write kappa 2 derivative equals to nu divided by gamma of 1 minus integral. Okay, when tau is 0, s is 0, and when tau is x, s is 1. Integral 0 to 1 x the nu minus 1 divided by x minus xs to the alpha times x ds, and we can write it x to the minus alpha 1 times 1 minus to the minus alpha x ds. X to the nu minus alpha plus, we can write x to the nu minus alpha. Integral 0 to 1. We should have 1s here, and I don't know, is that x? Tau is x. Where is it? X to the nu minus is correct. X. Oh, okay. Here, we have tau. Because we have f prime of tau, f of x is x to the 2. So here we have tau to the nu minus 1. And here we have tau. And suppose that here by changing variable of tau equals xs, we have here x to the nu minus 1, s to the nu minus 1. Okay. So in this part, I should write s to the nu minus 1 ds. For x, we have this term, it's correct. And for s, we have 1 minus s to the minus alpha times s to the nu minus 1 ds. And we know that we can write it like this. So it is, from the definition of beta function, is beta of 1 minus alpha and nu. So finally, we have nu times x to the nu minus alpha divided by gamma 1 minus alpha. And from the definition of beta function, we can write gamma 1 minus alpha. Gamma nu divided by gamma nu minus alpha plus 1. We can omit these two terms, and we know that gamma nu is gamma nu plus 1. So we have gamma nu plus 1 divided by gamma nu minus alpha plus 1 x to the nu minus alpha. So the computational derivative of order alpha of x nu can be obtained from this equation. For obtaining the approximation of fractional differential equation, we use this equation, this property, and this property a lot. And we can obtain some operational matrices of derivative and integral by using these two properties. Okay. Show that, yeah. The computational derivative and Riemann-Liouville integral satisfied in this theory, in this property. The Riemann-Liouville integral, fractional integral of order alpha of the kappa 2 derivative of order alpha of x equals to this. It's not only this term. For fractional calculus, we have this term too. Okay? Also here, we have two more definitions. The left-sided and right-sided Riemann-Liouville integral. And here we have this definition. The left-sided Riemann-Liouville. The left-sided Riemann-Liouville integral of order mu of f can be obtained from this integral. Here we have xl integral from xl to x. And the right-sided Riemann-Liouville integral of order mu can be obtained from this equation, integral from x to xr. So we have here the bond for integral like this. And we know that gamma here is gamma is a gamma function, and we know that about. And also here we have another definition, Riemann-Liouville differential, fractional differential of order mu. Before I told you a kappa 2 derivative of order mu or alpha. Here we have Riemann-Liouville. Left-sided Riemann-Liouville derivative of order mu is the inverse operators of Riemann-Liouville integral of order mu and can be obtained from this formula. You can see here we have the derivative of this integral, but for kappa 2 derivative we have here the derivative of f of s, and it's the difference between Riemann-Liouville and kappa 2 derivative fractional differential equation, fractional derivative. And also the right side, the Riemann-Liouville fractional derivative of order mu, we have this property. Also, we can, the left side and right side kappa 2 derivatives such as this, the only difference is here. Okay. The left side and right side fractional derivatives of Riemann-Liouville and kappa 2 derivative, kappa 2 type, satisfy in these following properties. The difference between kappa 2 derivative and Riemann-Liouville derivative of order mu for left side and right side can be obtained from these equations. Finally, we have another property, the Riemann-Liouville, the left side Riemann-Liouville derivative of order mu plus lambda equals to the Riemann-Liouville derivative of order mu times the Riemann-Liouville derivative of order lambda, and we can change these two terms. Okay. Now I want to show you some left-sided and right-sided kappa 2 or Riemann-Liouville derivative of some functions. For example, we want to find this. Riemann-Liouville. Riemann-Liouville fractional integral of order alpha of this function, e to the minus lambda x. We want to find it from the definition of Riemann-Liouville fraction, the right-sided Riemann-Liouville integral of order alpha. We know that it will be 1 divided by gamma alpha integral x to infinity to minus x to the alpha minus 1 f of 2. Here f is this term, so we have e to the minus lambda times 2 d2. This equation is important us for Laguerre polynomials when we want to obtain the polyfractonomial Laguerre. We use this property and we can obtain the polyfractonomial of Laguerre. Okay, now here by changing the variable 2 minus x equals to s. So we have here d2 equals to ds. We can write it equals to 1 divided by gamma of alpha integral. When 2 is x, s is 0, and when 2 is infinity, s infinity. We change this integral from x to infinity to from 0 to infinity. 2 minus x is s to the alpha minus 1 times e minus lambda times x plus s. And d2 is ds. And we can write it alpha. We have here ds, so we can write e to the minus lambda x integral 0 to infinity s to the alpha minus 1 e to the minus lambda s ds. And you can guess we want to use from the definition of gamma function. We have here integral 0 to infinity, and here is like gamma function, and it equals to gamma of alpha times lambda minus alpha. It is very simple to find it by the simple changing variable. You can find it. So here we have lambda to the minus alpha divided by gamma of alpha times gamma of alpha e to the minus lambda x. We can omit this and we have lambda to the minus alpha e x. And we find the right-sided Riemann-Liouville integral, fractional integral of order alpha of this function. Okay? And the next example that is important for the Laguerre polynomial is this. The Riemann-Liouville, the right-sided Riemann-Liouville fractional differential of order alpha of e to the minus lambda x. From the definition, we know that it can be obtained from this integral d. If we have kappa 2 derivative, we have here, for example, f prime x to infinity f of tau divided by tau minus x to the alpha d tau. Like that part, we can use the change of variable tau minus x equals to s, because we want to use the definition and the definition of gamma function, and for gamma function we have here integral 0 to infinity, and it's the reason that we use this change of variable. We have d to ds, so here we have minus 1 gamma of 1 minus alpha integral 0 to infinity e to the minus lambda tau is x plus s. And tau minus x is s to the alpha. So here we have here we have integral respect to s, so we can write the derivative of e to the minus lambda x times integral 0 to infinity s to the minus alpha e to the minus lambda s ds. It is the gamma function of 1 minus alpha, and it has a coefficient 2, alpha minus 1. It is very simple to obtain it by the simple change of variable. And here we have minus the derivative of this function with respect to x, minus 1. Minus lambda, it will be lambda, yeah, e to the minus lambda x divided by gamma 1 minus alpha lambda to the alpha minus gamma minus alpha, and we can omit this term, and here we have lambda to the alpha e to the minus lambda x. So the right-sided Riemann-Liouville derivative of order alpha of this function can be obtained from this term. Okay, we have a 10-minute break and then continue. In this section, I want to talk about function approximation. Suppose that f of x be a continuous function which can be expanded in terms of orthogonal polynomials. Here, suppose that phi j of x is a orthogonal polynomials. So we can approximate f of x by this summation. Series from from 0 to infinity cj phi j of x. The coefficient cj can be obtained by the inner product, and it is 1 divided by hj. Here hj is integral a to b. Phi j are defined in this interval. A to b, the weight function. For example, we know that the weight function of Hermite polynomials is e to the minus x to the 2. For a Laguerre polynomial is e to the minus x, and for other classic polynomials times phi jx to the 2, and hj is from this equation, and cj is equals to this part times this integral f of x times phi j of x, and here weight function. Okay, in practice we use only n plus 1 term of orthogonal polynomials, and we can write this series as it's equals to C transpose times phi of x. Here C is a coefficient vector and phi is a base function, is a base function, or is a vector of base function. And we can choose, for example, Legendre polynomial as a base, or other polynomials, orthogonal polynomials or non-orthogonal polynomials. Here I want to show some properties about only orthogonal polynomials. Here we have a theorem, and it is, suppose that phi of x be a shifted Legendre polynomials on interval 0 and 1, because we know that Legendre polynomials are defined on interval -1 and 1. And now, because next I want to use them for some example that are defined on interval 0 and 1, I use this definition. And also, suppose that nu is bigger than 0. We have these properties for fractional derivative of order nu. The derivative order of nu, here we have a kappa-2 derivative of nu of phi of x. Here phi is our polynomials, orthogonal polynomials, for example. Here is a shifted Legendre polynomial. It can be Chebyshev polynomial. Can be obtained from this equation. D to the nu. D to the nu is a operational matrix of derivative, of fractional derivative, and we know we want to know that what is it. Okay. We know that Legendre polynomial of order I of x has this series expansion, k from 0 to I minus 1 to the I plus k I plus k factorial x to the k I minus k factorial k factorial to the 2. The series expansion of Legendre polynomial on interval 0 and 1. And also we know that Legendre polynomials on interval 0 and 1 respect to the weight function equals to 1 p I x p j x dx are orthogonal, and this integral can be obtained by 2I plus 1. For integral minus 1 to 1, we have here 2 Kronecker delta of I and j. Okay. Now we want to find this. Then the fractional derivative of order nu of pi of x. We want to find it from we have an example for kappa-2 fractional derivative of x to the, for example, nu. We have this d nu of x k. We prove it equals to 0 for k less than the ceiling integer part of k and k factorial gamma of k minus nu plus 1 x to the k minus nu for k bigger than or equals to the ceiling integer part of y. So we know that for here we have pi, yeah, we know that this derivative fractional will be 0 for I from 0 to ceiling part of nu minus 1. Because of these properties, we know that when k is less than from this, it can be 0. So we should consider only this section. Okay. The capital derivative of pi of x. I want to find it. It is sufficient. We find the capital derivative of this series. So I can write it series from k from 0 to I minus 1 to the I plus k, I plus k factorial divided by I minus k factorial to the 2, the capital derivative of order nu of this part, x to the k. And from this property that we proved it, I can write it k factorial divided by gamma of k minus nu plus 1 x to the k minus nu. Instead this part, I can omit this, and so we have this series. K factorial gamma of k minus nu plus 1 x to the k minus nu. Okay, here I want to approximate this part by using the legend polynomials. So we can write x to the k minus nu equals to, okay, I should write here, I said that k should be bigger than or equals to the ceiling integer part of nu. So here I should write k from ceiling integer part of nu to the I. Okay, now I want to approximate this part by using the legend polynomials to find the operational matrix. So I can write x to the k minus nu equals to j from 0 to n b k j from the approximation theory p j of x. And from the definition we know that b k j can be obtained from the inner product. So we have b k j equals to 2j plus 1 integral and I say integral and write series integral 0 to 1 p j of x to the k minus nu dx. For obtaining this integral, I use again the series expansion of legend polynomials in this part, and I want to find the coefficient of bkj. So we have because j equals to 2j plus 1 series L from 0 to j. I use only the series expansion of pj minus 1 to the j plus L j plus L factorial j minus L factorial L factorial to the 2 integral 0 to 1 x to the k plus L minus nu dx, and it is a simple integral, and I can write it 2j plus 1 summation L from 0 to j plus L divided by k plus L minus nu plus 1. It's the answer, the integral. So, because j obtained as this, and we here we want to approximate x to the k minus nu by using the Legend polynomials. We find bkj from here. So by substituting this equation and this equation in this equation 1, 2, and 3 by replacing equations 2 and 3 in 1, we have, I write the final equation series from g from 0 to n, k from the ceiling part of nu to I, theta I, j k, pj times pj of x. By substituting theta I, k, j, I, j, k can be obtained by substituting 2 and 3 in 1. So here we can write d nu of phi x equals to d nu, a matrix of order n plus 1 times n plus 1 times phi of x. Phi of x is the vector of Legend polynomials p0 of x, p1 of x until pn of x transpose. So we can obtain this. And here you can see the elements of these matrices. Here we have 0 because I told you for k from 0 to ceiling integer part of nu, this summation is 0. And for the last rows, we have these elements. You can find these operational matrices of derivative for other polynomials too, for Chebyshev polynomial, for Laguerre, and for Jacobi polynomials too. The process is similar to for the Legend. And here I write Tijk in details for you. Okay. In this section, I want to use I want to use orthogonal polynomials for solving fractional neutral delay differential equation. We investigate these equations and we use etap-based function for solving them. Now I want to use Legend polynomial or Jacobi polynomials. We know that Legend polynomials are a special case of Jacobi polynomials for obtaining the solution of this fractional equation. Here we have the fractional derivative of order alpha of x of t, and the function is this. The delay term are this part and this part, and also we have the fractional derivative here in the function too. The initial condition is x0, and here we suppose that the fractional order be between 0 and 1. Okay, and x of t is a L vector function, f of t is 2, is a vector function, and delay term delta 1, delta 2, and x of and tau of t and phi of t, all of them we suppose that are continuous function. In this section, I want to use Jacobi polynomials as a base function. We know that Jacobi polynomials has this series expansion. Okay, and they are orthogonal respect to this weight function. We suppose the base, our base is this equation. Its member are Jacobi polynomials of order nu and beta, and we approximate the solution of fractional differential equation by these equation. Here we use least square approximation to find the solution of equation. Okay. By using the definition of Riemann-Liouville integral fractional of order alpha, we can find these operational matrix of integral like the last theorem for derivative. We can obtain it easily. And we can find this equation. Here in this article, we don't approximate t to the k plus alpha in base of Jacobi polynomials or, for example, Legend polynomials. Because we want later use collocation and collocation method, and we remind it in this manner. Okay. By using the least squares approximation of fractional derivative of order alpha, we can write the derivative of order alpha of each xi can be obtained from this equation. And for x of t, our vector, we can write it in this like this equation. Here c hat is a L times n plus 1 times 1 vector, and g hat can be obtained from this equation. Here we have an identity matrix of order L times L. Here it's Kronecker product, and we know that it is a base function. By using the fractional integral differential equation, we can obtain this equation easily by substituting this equation in the main problem. We have this equation. Now we want to use collocation method, and by using the collocation node, for example, the roots of Chebyshev polynomials, or for example, what do you like? We can obtain the solution of fractional differential equation. And now we have an example, and then we investigate the error band for this method, this numerical method. First, I show you the error band, and then I give you an example. Okay, here we suppose that X be a member of Sobolev space with this norm. The norm of X in Sobolev space can be obtained from this equation. Also, we suppose that F and X, the derivative of X, fractional derivative of X, and delay terms, all of them satisfy the Lipschitz theorem. And we suppose that L1, L2, B are Lipschitz constant. Here we have a theorem. This theorem, you can see it in this book. A spectral method fundamental in single domain by Kanato, Hossain, Hart, and Jean. In this book, the error band for approximation of solution of differential equation by using different orthogonal polynomials is shown. Okay, we use this theorem from this book. Suppose that X be a member of a Sobolev space of order mu and XMG be the least square approximation of X. So we have this error band for X. For R between 1 and mu, we have this error band. I want to use this theorem to show, to obtain the error band of our method. In this section, we expand the derivative, the Kappa-2 derivative of order alpha of X by using the Jacobi polynomials. So we use the last theorem for the derivative of order alpha, and we have this equation. By substituting X, the exact solution of the equation of main equation, and the numerical xm is the approximation of X by using the numerical method, we can obtain the error band by this theorem. In this theorem, we can obtain the error band, and you can see it is simple and it's dependent on M. M is the member of a space of R I forget the member of R base. Okay, when M increase, the error decrease and it goes to 0. It's a good theorem, and by using the Lipschitz constant and the last theorem, we can obtain this error band easily. Okay, now I want to show you an example, a numerical example. Yeah, here. The result of the error analysis you can find on my papers about the fractional calculus, and now I want to consider this example. Here we have a three-dimensional time-dependent delay system. We have the fractional order of alpha of x1 is this function. Here we have delay term, the square root of sine of t. For the second equation, the delay term is the square root of t. Also e to the minus 2t. So we have different form of delay too. A state dependent and time dependent. Here is time dependent, and oh no, it's here I have only a state time dependent. We don't have a state dependent. And this equation. The exact solution of this example is for x1 we have sine of t2. For x2 we have cosine of t, and for x3 we have sine of t. By using the proposed method, by m equals to 7, we obtain the absolute error with the different choices of collocation points. Equidistant points, 0 of the Legendre and 0 of Chebyshev polynomials. And you can see the absolute error for x1, x2, and x3. Also, the next table is about the absolute error for this example by using multi-quadric approximation. Okay, I finished what I was going to tell you this session. If you have any comment or question, please let me know.